Hello, this is Christian Krattenhoft from Liverpool again. This is my second video of the day. I have been requested to solve the problem of solve one or more problems involving laterally loaded piles. I'll solve one problem. Again, just to give you a feel for how to set up the problem and some of the typical results. For the pile, I'm going to use this, to model the pile, I'm going to use this N prism tool that I introduced in the previous video. That's a discrete cylinder with N sides. And I'm going to, since this is sort of a quick example, I'm going to just use 12 sides for the to model the pile. And I'm going to put the base of the pile here at the origin, 0, 0, 0. I am going to have a radius of 0.5, so a diameter of 1 meter, and I'm going to make the height, I'm going to have 5 meters below ground and 10 meters above ground, so a total height of 15 meters. So that's the pile with 12 sides. And then for the soil, and I am going to use the box tool to basically define the soil. So we can do it in 2 goes, we don't have to, but let's just do it in 2 goes. So first the soil from the base of the pile, and let's make it something like 20 by 20, and then a height of 5. So here we have it, the soil pile, and you should be able to see the base of the pile. And then we would want some soil here as well below the pile, and again I can make that to a depth of 5 meters. So I enter a height of -5. So here is the complete problem, complete geometry. And what I now need to do is assign materials. So for the soil, I will again use the Tresca material. I'll say this is an undrained total stress analysis. Tresca material, make it a really kind of soft clay, an SU of 50. And I then need to get access to the part of the pile underneath the soil in order to assign material to that, and I can do that in several ways. One way is to basically hide this soil layer so that I now can get access to both parts of the pile, and I'm going to use the rigid material, and I'm going to say this is a concrete pile, so a unit weight of 23. And unhide that. I should say you can as well use this transparency. You can make it transparent, and in that way you can get access to the underground. Okay. Now, so that is it with respect to materials in geometry, standard fixities, and then I'm going to apply a load up here, a lateral load at the top of the pile, and I'm going to just rotate things like that, and I'm going to apply the load, a purely lateral load in the X direction. And I select the surface up here. I have unselected solid selection over here, so I can point to the surface and select just that, and then to features, multiply distributed load, X direction 1 and 0 in the other 2 directions. And you'll see now there is a problem because the loads actually point opposite to the X direction, but if you look closely, there is a local coordinate system that has appeared up here, again red, blue, green, and that local coordinate system is the default one used when assigning load to surfaces. But I can switch that to the global system, that is the system down here, so that we now have a load of 1 in the x direction, the global x direction. And that's it. And we are then ready to solve. It's a limit analysis, and we'll use the next element again, 1,000 of those, and we'll use 3 adaptivity steps as well. Run the analysis and let's see what happens. And you'll see here, if you look at the number of elements that's actually produced, that number tends to be quite a bit higher than what I have actually requested. So I request to start with 1,000 elements, and then to finish off with 1,000 elements as well. So in the course of 3 adaptive iterations, basically rearrange 1,000 elements. But you'll see that the actual number of elements produced tends to be quite a bit higher than that, something like 2,600 eventually in the 3rd adaptive iteration, and a collapse multiplier of 405, and that needs to be, of course, multiplied by the area of the pile, which is pi divided by 4 times the radius squared, and the radius is 1, so a load, maximum lateral load in this case, of 318.49 kilonewton. And if we look at the final situation, well, that kind of looks more or less as expected, if not exactly as expected. You can see there is potentially a bit of a problem in that the soil sticks to the back of the pile here. That is fully consistent with the model we have assumed, but it may not be exactly as expected. So we could have a look at the interface between the pile and the soil. Can hide that, and then we can get access to this pile soil interface. We can select these parts of the pile and then eventually apply a shear joint. And these shear joints are, for those of you again who are familiar with G2, it works exactly in the same way as in G2. So when I apply the shear joint, you see it turn green there. It basically, the material that's applied at the interface here is the first material in the list over here. So that is not necessarily what we want in all cases, and what I really should have done as well to start with is to duplicate the Tresca material. And let's make that some other color, say blue, and I can then choose a smaller SU at the interface here. Even I could choose 0, so a perfectly smooth pile, and I would then just have to select all of these again in order to basically apply this blue interface material. And call that Tresca basic interface. Okay, and I could of course, maybe I should even, you could say, do the same at the base of the pile. Again, the shear joint, that turns green because MC basic, the green MC basic is the first in the list, but I can make that blue, unhide everything, and we have the problem again. And let's solve. Let's see how that looks. As you can see, the soil and the pile actually separate here behind the pile. So the interface here is perfectly smooth, and we have this separation, which is of course on the safe side, as opposed to the case where we assume that we have a full bond between the soil and the pile. And as I've said before, these analyses do take quite a bit of time. There's just no way around that. 3D analysis is just a lot more time consuming than 2D analysis. So our strategy here with G3 has been twofold. First of all, use very accurate finite elements. We've developed some new elements, among them this mixed element, and secondly, use mesh adaptivity. And in that way you can actually, in far most cases, get away with a very moderate number of elements. So the solution we have done here, and again, there's a clear separation at the back of the pile here between the soil and the pile. And the limit load of 353, and if we compare that to what we had before, well, we have a fairly slight reduction in the limit load from 318 to 277 kilonewton as a result of modifying this interface. So there you have it. And I could of course have used more elements, and if I'd done that, you would have seen that I would have had a slight improvement in the limit load, but really not all that much. I'm quite confident of. But that's of course something that can and also should be verified. So see you next time.